Okay, recording now. That's good. And that's this thing here. So here you go. We have the lengths. We come up with all the lengths here. 4 different lengths from 25 centimeters to 1 meter. Mass of the pendulum is 1 kilogram. Acceleration of gravity is 9.8 meters per second square. And we're going to collect the values of the period for the pendulum for each of those lengths. Okay, so let's go there to our simulation. Period right in here. I'm gonna put it side by side. And we want to release the pendulum from 30 degrees. Let me pause first the simulation. 30 degrees. Right in here. Let's start the simulation. I'm going to start my watch at the maximum amplitude. Here you go. Right now. And then I'm going to wait for a full period. Once it gets to the full period, I'll stop right now. I'm getting 201 seconds. I didn't stop. I didn't, pause the simulation, but I did stop my watch. So period 201. Let's see what I got before. I got 204. It's very close. That's 1 meter. Good. Now we're going to shrink it to 75 centimeters. Here you go. I'm going to stop. Here you go. 0. Everything. My watch is set at 0. Everything is my watch, has already started, but because I paused the simulation, the stopwatch is not working, right? So let's do it this way. I'm going to start the simulation, wait for one full oscillation. Here you go, start. Because it's going to be 75 centimeters shorter than before, you should expect a period of less than 2 seconds. Go back and forth to full oscillation, stop right in here. I've got, see, 171. 171, 3/10 of a second difference. In our real life, like I said, we do not count a single oscillation. We count like 10 oscillations. We count 10 oscillations to get better results, better experimental results. The more oscillations we get from a real in a real experiment, the better your result ends up being. Now let's see, 75 centimeters. We are gonna go to half meter. Nope, not here. Right here. Good. 0. Start. And it's paused. The simulation is paused. Here you go. Back and forth and back. Right here you go. Stop right in here. 145. Shorter pendulum, smaller, shorter period. Now 0, they start the pendulum because everything is, oh, don't forget to decrease now to 25 centimeters. We go 30, 29, 28, 27, 26, 25, and can start the simulation. Watch for a full oscillation of the pendulum. The full oscillation is, here you go, right here, 104. Clearly, there is a decrease in the period when the length of the pendulum decreases. You can even plot this graph. Okay. Length in the horizontal, period in the vertical, insert chart. Okay, here you go. What you see here is kind of a square root relation. Okay, if you really want to know whether it's square root relation or not, you can come up with a log scale right in here. Not this one. No, not this one. Sorry, folks. You want the log scale in the horizontal. Not this one. Here you go. Axis option. You want, here you go. You want the log scale in the horizontal. Let's see what happens. Logarithmic scale. Yeah, when you do the logarithmic scale in the horizontal line, you get something that's more straight line. Okay, there's a reason. There's a very important way of plotting a graph. When we plot this relation in the log scale, I can repeat that. I'm going to repeat that in a different way so you understand better. Here you go. I'm going to insert. There's a little trick that we teach physics students on how to get the most data, the most information of your data. Okay, so we get. I'm in the wrong spot. Actually, I'm gonna do the following. I'm gonna get the log of the length. Okay, and take the log of this function right in here. Okay. Depending on the relationship between the period and the length, or one variable or another, we can visualize it in a linear fashion if we plot one of the variables as a log. Let's see what happens here. Here you go. I'm going to plot that as a log. We do get a linear relationship. Okay. And what else? What else we can do? I'm going to put here a trend line, okay, and display the equation on chart. Okay, you can see that it has a very high R² value just by making a log plot of the graph. This is slope that you see right here, 1.56369, right, is related to the power that we have there in the length. Okay, that's a little secret that we teach students. Okay, let's move forward now to the next one. But if you want to plot without having the log, you're going to see that there is a square root type of behavior right in here. Okay, I even can come up with a trend line, but in this case, don't put a linear trend line. In this case, put a power trend line, and look what we get for the power for the equation. We get something that's close to a square root. Square root is 0.5, right? Y is the period. Is the period right here. X is the length of the pendulum, and this power that you see here is close to 0.5. There is a less than 10% difference between this power that we got experimentally and what you expect that is the number to be as being half. Okay, 0.5 and 0.468 is 0.03 difference. 0.03 difference is less than 10% difference. 0.03 difference is 6% difference, around 6% difference. 0.03, yeah, 6% difference. a little bit more than 6% difference. It's an acceptable result. Let's go to the next one. Okay, the next one, the next activity here. That's the first part. We're going to repeat the investigation, but now in this case, we are going to adjust the mass of the pendulum only, leaving all other variables constant. We're going to do another new table. Let's go in Excel. Here you go. Mass. Let's take a look at the original table. That's the one we changed, yeah? It's gonna be this one right in here. I'm gonna copy the value. That's the parameter that we're gonna change through the experiment. The length and the acceleration of gravity will remain the same. Okay, here you go. I'm gonna copy that, and then I'm going to perform the experiment for those values. Here you go. Acceleration of gravity. I'm going to keep the length constant. Note that we already have, let me see here. No, okay. We have for 1 meter a mass of 1 meter, 1 kilogram, right? But I didn't put 1 kilogram here. So let's go ahead and collect the period for those mass and lengths. Repeat the experiment for change of mass. What you're going to find out is that there is no variation whatsoever in the period. The variation is very small. Go. So I'm going to increase the length of the pendulum to 1 meter. The mass, we're going to start at 1.5. Here you go, 1.5 meters, 1.5 kilograms. You know what, this time, we're going to do is like, here you go, this time we're going to use this, instead of using the introduction, now we're going to do the experiment in a quicker way. There's a more convenient way of performing the simulation, okay? There is this lab here, the energy tab. In the energy tab, the tab in the middle here, where we're using this one, in the energy tab, we can not only have the ruler, not only have the stopwatcher, and we also have this energy graph, okay? But we also have something very convenient that's called the period trace. In the case of the period trace, you don't need to worry about stopping and playing and stopping your watch. Let me show you what I mean about that. I'm going to display this guy by 30 degrees, okay? I'm going to release it. When you have a full period, let's see here. Where's the period? We're supposed to get, let me stop here, sorry. We didn't get what I want to get here. Let's see what's going on here. The period trace. Period trace mass. It didn't show the period trace here. Why is that? Let's see here. We're supposed to show the period of this watch. Where is that? The period of oscillation. Let's see. Is it possible that it's here? Or maybe it's here. Let's see. Okay. It doesn't show in that simulation for some reason. Yeah. Okay, so you gotta use the third tab, not the second one, okay? When we check the period trace in this simulation, for some reason that period watch, that time piece doesn't show up. So it looks like it's a bug in the simulation here, in this middle simulation. If you look, okay, you gotta choose this third simulation, the third one in the lab, okay? And now notice what happened. When I click the period timer, this period timer shows up here. You don't need to use the stopwatch. This period timer is very convenient. It's very convenient. Let me show you. I'm going to set the length to 1 meter, right? The mass is going to be 1.5 kilograms. The acceleration of gravity is 9.8. I'm going to pause the simulation, put the amplitude to 30 degrees, start my period timer, and this guy here is going to measure exactly what is the period of simulation without you have to use the stopwatch. Okay, watch is going to happen. I'm going to start the simulation. Here you go. That's the period of the oscillation, 2.04 seconds. 2.0410 seconds. So use the third tab here at the bottom. There you go. 20410. Let's see if anything changes. 20410 doesn't change much, right? We can do that several times. Okay? So go ahead to your spreadsheet. 1.5 kilograms. 2.0410. Here you go. Next is 75 centimeters. 75 centimeters. Here you go. We can start again. Here you go. 17693. 17693. 1.7693. Next is half meter. We go down to half meter. Wait a minute. I'm sorry. I changed it. I changed the length instead of the mass. Let's go back here. Let's go back to 1 meter, right? We gotta go to 75 kilograms, 0.75 kilograms. I'm supposed to change only the mass. Okay, here you go. Gotta correct this second data point here. It shouldn't give much of a change. 2.031, 2.0318, 0.75 kilograms. Let's do that again. Let's see if it changes anything. 2.0318. The difference is 100th of a second. Let's do half kilogram right here. Start. 20318. Oh, same as before. 2.0318. And we're gonna go to 0.25 kilograms. Start. 2.0318. Oh my, that doesn't change much. Let's go back to 1.5. Let's see, I'm gonna just repeat this first one at the top. I thought it was interesting. We got exactly the same numbers here for this one. 2.0318. Looks like the simulation is stuck with this value now. Okay? But what I got before, when I was preparing that video, was something slightly different. Like that. This time I got everything being the same value. Okay. And then you can see by changing the mass, the period doesn't change much. In real life, you're going to see a little bit of a variation here, but nothing that is, important enough to justify the conclusion that the period depends on the mass. Okay? So going back to that equation, equation that we saw there in the handout. Let's take a look. Here you go. There is no dependence on the mass. The period does not depend on the mass of the simple pendulum. Okay? Let's do one more. Now we are going to repeat the experiment at different planets for different acceleration of gravity. So you can see that there is a dependence on the acceleration of gravity. Going back to the simulation, here you go. And also to your spreadsheet. I have my spreadsheet right in here. The third spreadsheet, mass, length, gravity, and the period. Now I want you the period, to the right of the acceleration of gravity. Put this way. There's a reason for that. Why is that? Because I want to plot the period against the g. Okay, and the g, I want the g to end up in the x-axis. Let's take those two. Here you go. Those two values are going to be constant. What's going to change is this one here, and then I'm going to get different periods for the g, because there is a dependence on the g. Let me get the values in the previous experiment. Here you go. I want to get. We're going to do 70 centimeters. Okay, so here you go. Let's adjust that. Mass 25.25 kilograms and length 0.7 centimeters. I'm going to stop it. 25 kilograms, 0.7 centimeters, right in here. What are the options that we have here? We have, for the moon, acceleration of gravity 1.62. Let's write it down. 1.62. We can also use the acceleration of gravity on the Earth, right? 9.8. 9.81. Let's write it down. 9.81. Which other one do we have? Which other option do you have? On planet Jupiter, 24.79. And we can have a costume acceleration of gravity. Costume acceleration of gravity means we can use whatever we want. We have this planet X, but we do not know which planet this one is, right? But we can use the costume. I prefer that we use the costume. And we adjust here what acceleration do you want. Okay? In my case, I use this acceleration of gravity here, 3.72, which is the acceleration of gravity of Mars, on the surface of Mars. Okay, so let's double check with the internet. Here you go. Acceleration of gravity on Mars. 372 one. Okay. So here you go. 3.721. It's a matter of getting the period right now. Perform the experiment, the simulation for the period. Here you go. We're going to start with the moon, 1.62. It's pause. We're going to start at 30 degrees right in here. Here you go. That's the period timer. Start. Here you go. Good. 4.2021. 4.2021. Next, we're going to do for the Earth. 9.81. Here you go. Did you know? See when I change to the Earth? Here you go. The period, what happened to the period? It's much faster. Now I want to change to the moon. Here you go. See that on the moon? On the moon is much slower because the acceleration of gravity is lower. If we go for the Earth, here you go. The period is larger, right? And let me pause the simulation again. I'm going to release it from 30 degrees amplitude. Start my period timer and start my simulation. Here you go. I see 1.7076. 1.7076. The period on Earth of this pendulum is shorter by almost 3 times. Almost, I would say 2.5 times. Then we go to Jupiter. We perform the simulation for the planet Jupiter. You see it again? What happened? I switch it from Earth to the moon, from Earth to Jupiter. Okay? And the period much shorter, right? Let's pause the simulation. Start the period timer. Start the simulation. Here you go. 10742. 1.0742 and finally 3721. 3721. Here you go. Three seven two one. 372. Here you go. Pause. Right in here. Let's pause, start the period timer, start the simulation. 27730. 2.77. Did I say 30? Yeah. 30. Okay. We can plot the period against the acceleration of gravity, and you can see that the period decreases with the g. Okay? Decreases with the g, what does it mean? It means the velocity of the pendulum is faster. On the average, it's faster. If we put a trend line for a power trend line, we should get something that is the negative square root. And that's exactly what I got. Negative 0.5. Okay. So that's what we have here for this lab. Okay, everybody's present, right? Yep, everybody's present. You folks are going to be graded according to your attendance to this lab, to the simple harmonic motion. And you don't need to turn in any lab report for that. And then what are we going to do next? What we are going to do is the law of gravity. That's going to be the next activity. Let's make sure we didn't forget anything else. And here you go. That corrected. Make velocity and acceleration. You don't need to do that part. Yeah. Okay. Lab questions and calculation. You can perform that on your own, right? That is, we're not going to do Hooke's law. We're not going to do this part. We're running out of time, and we need to do the next lab. So here we go. 145. We still have another Let's go for another half an hour before we have another break. Okay, so open VR Lab 10. Here you go. VR Lab 10. Newton's law of gravitation. For this, you must turn in a report for this activity. You must turn in a report. No report for the simple pendulum activity. Law of gravitation. Universal law of gravitation. Simple pendulum activity is lab 9. Here you go. Simple pendulum activity, we're done with that, but they're going to do that right now. This one you turn in at the last day of the last meeting. Let's get that. I'm going to close this one. Another one, I don't need it. We need this one right in here. Okay, and let's take a look at the theory behind that. Okay, oh yeah, let me copy and paste this one. This belongs right in here. April, let's see, today's the 28th. I'm going to erase circular motion, we don't need that. Okay. No report for lab 9, right? I'm not going to repeat that because I already wrote it down. We don't need that. I already told you when this one is due. Please download virtual. Please download Virtual Lab 10 handout. You have just a reminder, right? You have to turn in only 8 reports. You do not need to turn a lab, no reports for the following labs. Let's write that down. No reports for the following lab activities. Lab 1, Lab 9, 11, and 12. You must attend these meetings to get a grade, to grade you on these activities. Keep tabs on whether you're attending the meeting and participating, and at the end of the semester, take the average of all your report grades and assign this average to the activities that you did not have a report. Okay, that's okay. Okay, so going back here, going back to our building blocks of physics. Basic quantity, there are 7, but you have to worry only about 3. Length, time, and mass. Primary definitions, there are only 2, position and force. The basic quantities are scalar quantity. The primary definitions are vectorial quantities. I covered that before, right? And what's the other building block of physics? The laws of physics. Right now, we study only 3 laws of physics, the 3 Newton's law of motion. Now I'm going to introduce you to the law of universal gravitation. Asimov must have covered that. The law of universal gravitation states that 2 masses attract one another according to the following equation, according to the following relation. It is a constant, the mass, the value of the mass of the first object, the mass of the second object, and d is the distance between them. So this force is inversely proportional to the square of the distance. This value g is an important constant of physics. You do not have to memorize this value, but just remember that this is a very small number. This is a very small number. Because it's a very small number, you need very large masses to produce a measurable force. Okay? Note C that G is a very small number. Because of that, you need a very large mass to produce a measurable force. Planetary masses, for instance. Planetary masses, for instance. I usually like to show my students a very nice YouTube video we have out there. Okay? The way we perform, the actual way, the real way in real life that we perform this experiment involves a device that's not shown here in the simulation. Simulation is not a real life thing, but at least it helps you understand how the force of gravity works. But let's go to let me show you first the concepts, and then we go to the real life experiment, okay? Go, I don't need that. Link, I'm gonna get it here. Illustrations. I believe, let's see, this one here. Let me see if I can get it. No, that's not the one I want. Let's see. Let me see if I can find a slide that I like to show you folks. Here. 300. Bear with me, it must be here. Here you go. Gravitation and apparent law. Okay, apparent weight. Must be this one here. Okay, let's see. I'm not gonna show you every slide that's here, but that's what you gotta know. Okay? What Newton's found out? Newton found out that when 2 masses are close to one another, they interact with each other. Mass 2 is exerting an attractive, and this interaction is an attractive interaction. The forces are attractive. Mass 1 attracts mass 2, and mass 2 attracts mass 1. Okay? Here you go. Mass 1 attracts mass 2, and mass 2 attracts mass 1. What Newton found out as well was that if the mass is smaller, here you go, m3 less than m1 and m4 less than m2, the force is going to be smaller as well. We are keeping the distance constant. That's one side of the coin. There is another side to this coin. It has to do with the distance. The force increases with the mass, but the force decreases with the distance. See that? The masses are the same, m1 and m1, m2 and m2, but the distance increased from d2 to d1, and the force decreased. And the relationship that we get is something like that, you know, directly proportional to the masses, inversely proportional to the square of the distance. With this constant here, constant factor big G. Okay, here's a nice illustration that we have. A big mass attracting a smaller one, and to ensure that this mass doesn't get stuck with the second one, we put some other masses here to even out the scale. Okay? That's not exactly how we do in real life. In real life, when we want to perform an experiment to determine this force, okay, to determine this relation here, we do a very neat experiment that was first done in the 1700s by Cavendish. Let's take a look. Cavendish experiment. Here you go. Wikipedia experiment. Cavendish. Wikipedia. Wikipedia. Here you go. Mark Cavendish. This guy here. No, that's not the guy. Henry Cavendish, that's him. Let's take a look. That was the guy that came up with an, you know, Newton discovered. Let me put down there in my notes, okay? Newton discovered the above relation. However, it was Henry Cavendish who measured the constant big G in the above equation. Newton knew that there was a constant of proportionality, but he did not know what was the value of this constant of proportionality. So we came out, so comes into play Henry Cavendish. Okay, so here we go. Let me see. Density of the Earth. Okay, Cavendish experiment. Let's go there. He made, in order to find out that value big G, Cavendish has to do the experiment, and he called it the density, the experiment of the density of the Earth. Here you go, let's take a look here. The experiment, right in here, that's how the experiment looks like. Okay, if you want to find out more about this experiment, take a look at this article in Wikipedia. It's a pretty good one. It's what we call a torsional scale. And here you go. Whether Cavendish determined G. Cavendish expressed his results in the terms of the density of the Earth. So because of that, scientists argue that Cavendish did not measure the gravitational constant. Actually, what he did was to determine what was the mass of the Earth. Okay, but it is his experimental apparatus that we use today to measure G. It is his experimental apparatus that we use today to measure G. It's a torsional scale. You can understand better this device with a YouTube video. Here you go. On the Cavendish experiment. There's a very nice, I like this video right in here. There's this video too. Let's take a look at both of them. Here you go, gravitational constant.
With MailChimp's Creative Smarts, simply enter your website. Get beautiful designs drawn from your brand.
Skip this guy. Here you go.
Hi.
Yeah, that's the one.
Welcome.
I like this video that this guy did. But don't watch everything. We gotta skip it a little bit here and there, okay? But you will understand how this experiment is supposed to be done. Notice that we have a ruler right in here. Okay, and what else we have that's we can hardly see? We have a string, a thread right in here that's attached to this horizontal beam. Okay, this is a copper string that undergo torsion. What's torsion? Oh, torsion is the following. Here you go. If you have this string, a string just like that, and I try to rotate along the axis of the string, I am applying torsion to this string. So that's the principle that Cavendish used to determine the constant of gravity. And that's the experiment we perform in real life to determine the constant of gravity. This guy did a very good job on how this experiment works in real life. We have very simple devices here. We have a ruler, which is a beam, and we have a copper wire that can be bought anywhere, and masses that we hang from the end. And we see this brick right here. This brick also is part of the experiment. It's a lead brick, very heavy lead brick. It is, what time is that right now? It's 2:41 right now, right? Let me check if you folks are still there. I don't hear anything from you. Here we go, and we can have our break soon. Let's see here. Madina, are you there, Madina?
Yes.
Okay, good. So you finish your graphs for the simple harmonic motion, right?
Yeah.
Okay, good. What about Dior? Are you there, Dior?
Yes.
Okay, good. Any questions, Dior?
No, I'm good.
Okay, good. Shreya?
Yeah, I'm good too.
Okay, good. So you go. Next is Bella. Are you there, Bella?
Yes.
Okay. Mark?
Yes, I'm good.
Okay, good. Next is George.
Yes, I'm good.
You're there, okay. Oops, let's put it here. Next one is Ruya.
Yes, Professor.
Okay, thank you. Everybody here, let me. Next is Andrea. Are you there, Andrea?
Yes, Professor, I'm here.
Okay, next is Bao.
Yes, Professor.
Good, thank you. So 2:42 right now. Let's have our little break now, and we'll be here until 4:20, which is another hour and a half. Okay, and I will show you when we come back. I'll show you this video of this guy. It's a pretty good video. I like it. The way he did. We're going to skip around a little bit, and then we'll perform the activity, the simulation that we have. Okay, so I see you at 3 o'clock. Break till 3 p.m. Like I said, I'm gonna post this video there in my YouTube account, and that's the video that I have from from someone else, another guy that has a different YouTube channel. So what are we doing here? Let me just remind you what I'm doing here. We are going to do this simulation one way, okay? And the way that the simulation is done is not the way we perform an actual experiment. So before we do the actual simulation, that just going to add you to the familiarity of the concept that we're teaching here, I want you to show you how do we measure the attraction between masses in the real world. And this guy has a pretty nice video. I'm not gonna show everything, but I'm gonna skip a little bit around. And here you go, Rich Lund.
To my classroom. And what I have behind me here is my attempt to reproduce the Cavendish experiment.
Here you go, the Cavendish experiment is a bar in which you have two masses, and this bar is suspended by a wire. In this case, the wire is a copper wire. And there is more. There's a little bit more to it. But that's just some part, a very large percentage of the setup, okay? So here you go.
For my setup, what I have are 2 meter sticks, which have been taped together. And on either...
Here you go, the wire, the copper wire right in here, hanging, wrapped around the meter stick. Those masses, they are going to be subjected to an attractive force by another mass that's not shown here yet, okay? It's a torsional pendulum. To measure the force of gravitational attraction is a very difficult experiment because the force of gravitational attraction is very small. Not the force of gravitational attraction of the Earth, but the force of gravitational attraction between common objects. Okay? The force of gravitational attraction between common objects is very small and very difficult to measure. But there are some tricks that you can do to try to amplify the effect of this force. The way that Cavendish found out is by doing the experiment with a torsional scale. Okay? Remember that what this experiment is all about. This experiment is all about producing a torque that's produced by a very small force. If you can use a ruler that's very long, even a small force is going to generate a big torque. That was the genius of Cavendish, trying to measure a small attractive gravitational force. And what I mean a small attractive gravitational force, it means a small force of attraction produced by objects of small masses, like those 2 weights that are being deployed here, okay? And those other 2. Let's continue going here.
Either end of these 2 meter sticks, held there with some paper clips, are 2 1 kilogram masses on each end. Now this meter stick is being hung by a copper wire, which runs all the way up to the top of this very large piece of wood, which I have separated out and have supported up on lab tables with some physical science and AP chemistry textbooks. I'm here on a Sunday, and I've let this hang here since Friday when I left the building. In trying to do some preliminary testings during the week that I set this up, I found that this experiment was going to happen on a weekend. During a school day, and even after students have left, there's so many people opening and closing doors in the building and moving through the hallways that plenty of air currents are produced.
Okay, do you hear what he said? This experiment is so sensitive that even air currents can interfere with the result that we get, okay? So he didn't want anybody around walking back and forth interfering with his experiment. That's what he's talking about. The air current produced by people walking back and forth can spoil your experimental results. Basically, that's what it is.
And this experiment is quite sensitive to air currents. Another physics teacher, Andrew Bennett, has put together some very good Cavendish experiments on video. I'm in fact...
Here you go. That's how the Cavendish setup works. You know, the same ruler, meter stick, masses attached to the end, and now we can see what you didn't see in his setup yet. He put two other masses that are attracting those two little masses. Because this ruler is suspended by a wire, this mass is exerting not only a force, a gravitational force of attraction, but is also exerting a torque in this whole system. This torque is doubled down when we put a second mass on the other side. And what you see right in here is actual gravitational attraction producing this torque
experiments
effect.
on video. I'm in fact inspired by him and wanted to retest the same idea out.
Okay, so Cavendish did that exactly, and he was able to correlate. He was able to find the force of attraction of those two masses, of this ball and the other masses hanging in there, with the torsional force that this wire applies to the whole system. It is possible to quantify the value of the torsional force that the wire exerts in the whole system. It's possible.
In my classroom, we can talk about gravity in many contexts of just falling objects, but also, what about an actual demonstration that can show students, yeah, all objects that have mass do have a gravitational attraction to each other, even though it might be incredibly weak. The Cavendish experiment should be able to produce those results. And so for the masses, Andrew Bennett, he used some bowling balls. I have access, though, to these. This is a lead brick.
Lead brick, very heavy. You know, I do not know where this guy got that stuff.
And I'll be massing this in a little bit here so you can see just how heavy we're talking about. But 25, 30 pounds, somewhere around there, I'm just guessing. Where did this guy get some lead bricks? Well, I know a guy who knows a guy. You know what I'm saying? Actually, I know people who work at the MSU cyclotron, and I was able to get these on loan. And so I wanted to make my own video, not trying to steal any thunder from Andrew Bennett. I think his are excellent. But since I knew I had access to some lead bricks, I wanted to try out this experiment with something that is even more dense than bowling ball material. Before we do that, though, let's mass these bricks and show you how heavy they are. I turned off and on the scale, so that way now it is re-zeroed out. So it's not even registering the mass of these plastic bags.
Don't let something like that
Put a
fall in
lead
your
brick
toe.
in. Okay, and it's holding. And we're at about 12.03 kilograms. Get a workout doing this. But it also, when it comes to the Cavendish experiment, it's not just about how much mass you use.
12 kilograms is something like 26 pounds, 26, 27 pounds. That was this lead brick weight.
It's also about how much volume it's taking up. If you had something really large and massive like a car, well, that also takes up a whole lot of volume. And when it comes to gravitational effects, it's not just about the mass, it's also about the distance squared between the two objects. So yes, you want something very massive, but you also want it to take up not too much space, so that way you can get the hanging masses over there on the Cavendish experiment to be able to get close to the center of mass of your objects. Lead is a pretty good option. Gold bricks of this size, I don't quite have the budget for that.
Yeah, he could have done the experiment with a gold brick as well. But a gold brick would cost, of that size, that mass, would cost something like $500,000. I was doing the math some time ago. Gold is so expensive, so he doesn't have this type of money, so he bought something that's cheaper, less dense as well.
Without further ado, the Cavendish experiment.
Wow, look at this. 94% of people believe company culture is important.
Here you go.
Here's the experiment in its entirety.
From the
And
top,
we're doing it from
and
two
from
angles.
the side.
The downward angle and, of course, the side angle. The clocks were not 100% synchronized for these two shots. They were just placed in there to show the passage of time. However, it appears that the digital clock looks about 20 seconds faster than the analog clock. And so what we're doing now is just getting some footage of the torsion balance and how much it's already moving. Just what the noise of the experiment is. How much is it already rotating clockwise and counterclockwise?
I'm gonna fast forward, okay, because there's lots of time here that we don't need to watch. Here you go. He's just looking at how much noise you have in the experiment. What do you mean by noise? The air current. How much the air current interferes with the experiment. Okay, so this guy can rotate back and forth because of those air currents, and eventually he puts the lead bricks.
Are placed in.
Here you go. Lead brick on one side, lead brick
First
on the
one,
other
then
side.
the other.
And again, this experiment is a long
And
one.
now we'll sit back and see if we get any effect.
The effect is so small that it takes time for the lead brick to attract those 2 kilogram masses. But it's moving. It's moving. Little by little. Yeah, you see it? Eventually, the masses either is going to collide against the brick, or the torsion in the wire is going to revert the motion. Here you go. Is it gonna touch? Is it gonna touch? It looks like it touched. Now it's gonna bounce back. Right? Bounce back. It's not just the bouncing back of from the brick, but it's also the effect of the torsion of the wire. Okay? That's producing this effect. So let's fast forward. Here you go. He's had, okay, it's going back again. Here you go. Very slow. Because the force is very small, and this force is being amplified by the ruler because it's producing a torque. The torque increases with the distance from the point of the distance of the point of application of the force to the axis of rotation, right? It's easier for me to make this ruler rotate if I apply a force here at the edge than if I apply a force here at this other spot. Now let's fast forward. There's more stuff down there. They have a better video. Here we go. Too much stuff. Okay, now
Here again is just footage of...
Here you go. What he's gonna do now is gonna repeat the footage that you saw, but at much faster speed.
separately, but at 30 times the speed.
So you don't have to sit down for too long to see that thing happening.
Here again is just footage establishing how much noise was already in the experiment. Lead bricks are placed in.
Here you go. See that? That's what you're supposed to see in fast forward mode.
Now again, 30 times the speed. Here's the same experiment from the side angle shot. Lead bricks are placed in.
Here you go. Oops. Go much faster, right? The reflection that you're seeing there is both the...
And let's see the experiment one more time from both of those angles. This time at 50.
The force due to the impact, and also the force due to the torsion in the wire that's acting against the gravitational attraction of the lead brick, of the 2 lead bricks.
50 times the speed.
Here you go. That's the noise of the experiment due to, here you go, due to the air currents, and then the effect of gravitational attraction by the bricks. Here you go.
So how'd we do? Well, take a look at the results. In getting the first preliminary motion of our torsion...
Okay, what you see here is not a quantitative experiment, but it's still impressive. It's still impressive, okay? What you see here is a qualitative experiment. A quantitative experiment can be done with a device that's sold out there that costs like $800 to $1,000. Much smaller than that, but that's something that anybody, even I, can put together in the lab, okay? Let's keep on playing. There's a
balance. We can see how far counterclockwise and how far clockwise it was normally moving. You can say that this is the amplitude of the noise in our experiment. Now, I placed the lead bricks, and did I place them within that amplitude? Yes, I did. I wanted to get it close to where the masses were, so that way we could get a pronounced effect, and I think we did. But what about the argument that, well, hey, that was just in the direction it was going to move anyway eventually, and aren't the lead bricks just stopping its movement of the naturally reaching that amplitude? That's a valid question, but also we have evidence in this footage very much that that's not at all the case. You can notice that the amplitude of the torsion balance, its maximum amplitude in the counterclockwise direction, is seen here at the start of the footage. Then it reaches the clockwise maximum amplitude of the noise, and then on its way back, that's when I'm placing the lead bricks into position. And as soon as those are in position, the torsion balance never reaches the counterclockwise maximum position of its amplitude. Not even close. As soon as the lead bricks are placed into position, the torsion balance, moving already away from them, appears to be slowing down pretty dramatically and then changing direction much earlier than it normally would in its normal degree of rotation. This acceleration, the deacceleration in one direction and then accelerating into the other direction, was a constant acceleration in the direction of the lead bricks. That constant acceleration was the gravitational force of the lead bricks on those two hanging masses on each side. The Cavendish experiment. Not a quantitative measurement of big G, that's not what we were attempting here. But is this a qualitative, visual demonstration that gravity exists between all objects? A very weak force, yet still one that we can detect even here in the classroom setting? Absolutely. Ladies and gentlemen, thank you for watching. See you next time.
Okay, so that's how this experiment is done in real life. And if you want to do the experiment, you can buy that device that I mentioned to you that costs anywhere between $100 to $800 to $1,000. It works better than this one, and we can do a quantitative experiment. But that quantitative experiment, that depends how you perform it, is going to last anywhere between 15 minutes and 4 hours. Okay, so the force is so small that it may require you to perform the experiment in 4 hours, even with a commercial grade type of device that we have out there. Now, any questions about that? So it looks like there is a student that left. Let me see who was that. So let me see. Yeah, we have only 8 students right now. Let me see. Madina, are you there?
Yes.
Good. Dior, are you there, Dior?
Yes.
Okay. Shreya?
Yep.
Okay. Bella?
Yes.
Okay. Mark?
Yes, I'm here.
Okay. Who left? Huh? George, are you there, George?
Yes.
Okay. Ruya? Is that Ruya?
Yes, Professor.
Oh, okay,
Yes,
good.
Professor.
Okay, good. Andrea? Let's see. Is that possible? There's Andrea that left. Yeah, there's Andrea that left, right? Bao is here, right? Yeah.
Yes, Professor.
Yeah. Okay. So that was Andrea that left. Let me put here insert. This one is gonna be lab what? Number 8? No, lab 9, and this one is lab 10. Okay, I'm gonna put here insert copied cells, and bow. Okay. Good. Okay, so if Andrea doesn't show up again, she's not gonna get credit for this lab report, okay? Okay, so let's go ahead and start the activity. Okay, so here you go. What we're going to do, we're gonna go to the link that we have right in here. Let's go there. Oops, the request page could not be found. Uh-oh, not good. Okay, so let's look for this. Let's try again. If it doesn't work, then we're gonna do something else, okay? I'll try for a second time. If you still have it, okay. So let's go PHET, Colorado. You gotta hunt down. You gotta hunt this. Quantum electricity, motion, sound waves, quantum, we don't need quantum, we don't need radiation, we don't need electricity, we don't need heat and thermal. I wonder, let's see, work, energy, and power, we don't need, oh, right in here, gravity force lab. There is another one, is a new one. You should use the new one. Let's see where, I believe it's sitting motion, yeah. That's what it is, in motion. If you uncheck motion, then it's no longer there. Okay? So look at this one. Here you go. Here you go. Like I said, this thing is not a torsional scale. This is not a simulation of a real life experiment. This is a simulation of a simple procedure of how you would understand the simple explanation of how the force of gravity works. Okay? So basically you're going to change the masses that you have right in here. You're also going to change their distances. See that? You can change the masses and the distance, and you're going to measure the force. Okay, that's what we're going to do. Mass can be changed right in here. For the other one too. Okay, so let's go the instructions that we have here. Gravitational force versus mass. Set the distance between the two masses to 9.6 kilometers. I made huge modifications here, extensive modifications, which is going to be posted there in my YouTube channel. Let's set the distances to 9.6 kilometers. That's not the one, right? Is this one right in here. 9.6 kilometers. Notice that the force here, go. Look at the force here. What happens with the force when I increase the distance? Decreases, right? We're talking about 9.6. Okay. Not this one. It's this one right in here. 9.6 kilometers. For the two objects, we start with a mass of 1 billion kilograms. 1 billion kilograms, here you go, 1 billion, 1 billion. We get this force 0.7 newtons. Okay? Read the magnitude of gravitational force and record the value in the appropriate column in the table provided. Okay? So here you go, we are going to make a table like that in Excel spreadsheet, but follow here my instructions. Do not put 10 to the 9 kilogram between parentheses below. Just write kilogram and log the actual number in kilograms. I'm going to show you how to do that. is going to be mass. We are going to change. What we are going to do? We are going to keep this mass at 1 billion, and we are going to change this one as we go along. That's what we're going to do. But let's come up with the spreadsheet to perform this activity. Right in here, lab number 7, and let's see, that's lab number 7. I want to come up with a new spreadsheet. Here you go, lab 10. Lab number 10. Right here, I'm going to zoom in. I like to freeze the panes. Here you go. I froze my panes here. I can go up and down. I think I'm gonna freeze this way. And freeze it. Oh. And freeze again. Here you go. What are we going to do? I'm going to put mass number 2 right in here and kilograms between parentheses. Always use the units. I am going to put a subscript in my mass. Let's see what it uses. Let's see if it uses capital M, right? Yeah, use a capital M here, so I'm going to put a capital M in my and then you're going to put the force and then the unit of force. I'm not going to put the unit of force for you. You should know that. You start at 1 billion. 1 billion is what? 1 billion is, you know, you can write like that. 1e to the 9. Okay? That's 1 billion. A million is e to the 3rd power. Wait a minute. 1,000 is e to the 3rd power. A million is e to the 6th power. A billion is e to the 9th power. That's one way of writing down a billion in Excel. There's another way. There's a second way. Okay, I think this one is easier, but the second way is more intuitive. The second way, you press the equal sign, write down 10 power 9. That's another way. And it should display like that. And then what else are you going to do? Right? You're going to increase the mass from 1 billion to 10 billion. That can be done easily. Okay, 2 billion. Here you go. E9. Here you go. Click, highlight, and drag so you can get to 10 billion. 3, 4, 5, 6, 7, 8. Oh, wait a minute. He's not doing it. That's bad. Huh. Yeah, for some reason he's not doing it. I hate that. Okay, let's put 3 here. Let's see if he does now. No, he still doesn't do it. What a shame. Oh gosh, sometimes those things work, sometimes they don't work. What a shame. You know the way you're gonna do it? We're gonna do like that. 1, 2, 3. Now it should work. Yeah, see, this one works for some reason, but the other one doesn't. Huh. And now what I'm gonna do, I'm going to make, you know, this guy, this times e to the 9. Uh-oh. Okay, so I gotta do like that. Instead of e to the 9, you do 10 to the power 9. Here you go. Now we should have it from 1 billion to 10 billion. And then write down the force. The force that you record in that simulation. Now what this thing keep on getting in here. I don't want that. I want this one. Here you go. That's the force you should record. 0.7. We are going to see the effect of the masses in the force. 0.7 newtons. I didn't put the unit there at the top, but you should do that yourself. Let's go to, and what else I'm gonna do? Here you go. I'm gonna shrink my window size here. I'm gonna try to display both the simulation and my spreadsheet. I'm going to increase my mass number 2 to 2 billion, and here you go, we get 1.4. Next, 3 billion, 2.2. Next, 4 billion, 2.9. 4 times more mass, it's almost 4 times more the force. 4 times 0.7 is 2.8, right? A small difference here. 5% difference. 5 times 5 billion. 3.6. 6 billion. 4.3. 7 billion. 5.1. Next, 8 billion. 5.8. 9 billion. 6.5. And finally, 10 billion. 7.2. Okay, so that's the little trick that I did to get things going more quickly, right? I put the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's make this table look nice. Put dark borders. And let's see what else he wants us to do. Repeat step 2 until you reach 10 billion. We did that. And record the corresponding values of the magnitude of gravitational force on mass 1. Referring to the equation for the gravitational force, we notice that, okay, so we're changing M2. Everything else right in here is a constant. Is a constant. So if we plot the force of attraction in the y-axis and the mass 2 in the x-axis, we should get a straight line with a slope and a intercept. The intercept in this case should be 0 because according to Newton's prediction, there is no intercept for his equation, right? So that's what we're going to do. Make a graph for the gravitational force versus M2 for the data you recorded in the table 1. Don't forget there is some mistakes here, okay, that I corrected. You must get a linear graph in step 6. You must get a linear graph in step 6. Yeah, okay. So we are going to plot it. Let us plot my graph. Highlight those two. Insert. Scatter plot. Yeah, we do get a linear plot. I want you to, do a nice job about this axis here. There is no need to have 2 decimal places there. It's unnecessary. So you click here in the x-axis, you go in number, you must make sure you click here in the bar chart, you go in the numbers and decrease the number of decimal places to 1. So we save space in there. We don't need to go all the way down to 1.5. We can go all the way up to 1.2. And we don't need to start at -3, right? We can start at 0. Then we change it also here to 2 instead of 5. Okay, I like that better. bold face. Remember, you gotta do a nice job here. Here's the force of gravity, attraction, attractive force. We will have to put the labels, add chart element, axis title, primary horizontal, primary vertical. Oh, what did I do here? Something wrong. I did something wrong here. Add chart tag. Okay, primary vertical. Make a little bit larger, you know, maybe 16. Here you go. First, put the, oh, don't forget to get capital F here on this one. You do the same thing, put 16 size, and should be mass number 2. Mass 2, parentheses, unit, and subscript. Subscript right now. If you want to make it look nicer, you can put italics here. You can put italics here as well. And what else you're going to do? You are going to get the trend line of this plot. Here you go. I got my trend line, but I don't want, see, it doesn't have an additional decimal place in there. Let's see if I can increase the number of decimal places. Format trend line label, that's what you do. Go to format trend line label. Instead of general, you put number. No, you don't want number, sorry. You want scientific. Okay? And now we got 2 decimal places there. 7.24. The slope is 7.24 times 10 to minus 10. That's the slope of this equation. Am I going too fast? We have less than 1 hour to finish this activity. We have, what, 40 minutes? So we plot, we got the equation. Now you go ahead and you write down the slope and you write down the intercept that you got. Let's go back again here to the graph. There is this intercept here. This intercept, by the way, is a small value, okay? Why, you know, it's like 1.33, is 0.0133 times 10 to minus 2. This guy here, don't forget to put the units of the intercept. Don't forget to put the units of the intercept, please. Otherwise, I'm going to take it out, take points out of it. So when you write down your name, oh, with the appropriate units. With the appropriate units. Put the number and the unit. Not just for the slope, but also for the intercept. Okay? So this number that you got in there, I can tell you that's small because it should be comparable with the force that you are getting here. This number here is a little bit more than 1%. It's almost 2% the smallest force value. Force value is 0.7 newtons. This guy here is a little bit less than 2% than the smallest force value. Okay? And the slope is also a small number, and it should be comparable to something that I'm going to tell you right now. I want to know if you're following that. Did you get your spreadsheet done there? And your graph plotted? If you don't say anything, I'm going to assume that you got everything. All right? Let me get someone here in a random fashion. Here you go. Mark, did you plot your graph, Mark? Is Mark there? Hi, Mark.
Yes, I'm here.
Okay, do you plot your graph?
Yes.
Okay. So let me get someone else. Here you go, right in here. Dior, did you get your graph? You plot your graph, Dior?
Yes.
First graph. Okay. So let's move forward now and find.
Excuse me, Professor?
Yeah. Yeah, go ahead.
Could you show one more time how you changed the trend line equation to that scientific
Okay. Yeah.
format?
Let's do that. Here you go. My plot is where? My plot is here. Okay, so here you go. Let me see if I can. No. No, I cannot do that. Let's go back. The way you do it, who is that? What's your name? Help me out here.
Medina?
Okay, Medina. Okay, here you go, Medina. You click on this equation here. Make things highlighted. Make sure it's highlighted. Okay. Right click it. Format trend line label. Okay, and then this window should show up with the number. It was originally on general. That's where it was originally set to. You want to change it to scientific. Okay? And when you set to scientific, it automatically shows you with 2 decimal places. Make sense?
Yeah, got it. Thank you so much.
Okay. So I'm going to write down your slope with the proper units, and you're going to write down your intercept. Don't forget the negative part. If I get a negative sign, I did get a negative sign, right? If you get a negative sign, you should write down everything with the negative sign in the intercept value. Going back to the equations for the G experimental, okay? So let me walk you through how you find the G experimental. You find the G experimental from this equation right in here. This A is the slope. This one here is what the theory predicts. Okay? The slope should be equal to GM1 divided by D squared. Okay, and then you get the G experimental from there. Let's do the calculation together. I will get that here. Here you go. I'm gonna do is this guy. My favorite software, Live Math Maker. Here you go. That's lab 10. G M1 divided by D squared must be equal to the slope that we got from the graph. Okay, and we want to find out this value here, G. This G is going to be my experimental G. It is my experimental G because we performed the experiment to find the slope value. My D, what's the value of the D? The D is 9.6 kilometers, right? But 9.6 kilometers is 10 to the 3 meters. It's 9,600 meters. M1 is equal to what? M1 is equal to 1 billion kilograms. Here you go. And my slope, what's my slope is equal to? Go back there to it's equal to this value. Don't forget to put the units as well. I'm going to show you what the units are. Here you go. 10 to minus 10, and then what's the unit of the slope? You must put the units there. I'm going to put the multiplication sign, and I'm going to write down the units here in this question mark. Let's take a look at the graph. The units of the slope is the units of the force divided by the units of mass. is rise divided by run, is Newton divided by kilogram. That's what the unit of the slope is all about. Okay? Newton divided by kilogram. Let's save space by putting those values side by side. And we are going to get the experimental value of G. After getting the numerical value of the experimental G, we are going to compare it with what is written down in our books. Okay, so let's see if we can get this thing calculated, expanded first. Okay, that's what I'm getting. Newton meter square over kilogram square. 10 to minus 11. Is that what they say in your book? In your book, in your handout? Here. Must be more here at the top. Here you go. That's what I was given. That's the theoretical value. That's my experimental value. Very close, right? Even the units are correct. Newton meter square per kilogram square. Okay, now what else? Graphing, intercept, good. And yeah, now we're going to do the finding gravitational constant. Yeah, calculated value, equation for G. The equation for G is this one here. The calculated value for G is this one right in here, for me, right? Maybe you're gonna get different values, okay? That the calculated value of G agrees close enough with the given one. If not, work with your group to determine why not. We did gravitational force against mass, mass number 1. Now we're going to do gravitational force against the distance. Can we move forward? It's 3:50 right now. We have another half hour. Let's see. I presume that this is the last part of the experiment. Hopefully it is. Yeah, that's the last part of the experiment, so we can finish it today. Okay, we're going to do a second table and a second graph. We're going to set the two objects, the masses of the two objects, to 1 billion. 1 billion here, 1 billion here. Set the distance between the two masses to 2 kilometers. 2 kilometers, here you go. Oh, too close. Here you go, 2 kilometers now. And look at the value of the force, 18.5 newtons. Last time I calculated how much is 1 billion kilograms, okay? I'm trying to remember what was the exact value. I believe it was around like 3 Empire State Buildings. That's what 1 billion kilograms is all about. Let me see if I wrote that down here for you. Yeah, it doesn't look like I wrote it down, but it's something like that, okay? 1 billion kilograms, if my memory doesn't fail, is like 3 Empire State Buildings. The mass of 3 Empire State Buildings. So let's go back. What we're going to do, we're going to increase the distance between the masses. But don't write down the distance in kilometers. Write down the distance in meters, okay? Another table, from 2 kilometers to 10 kilometers. From 2,000 meters to 10,000 meters. But don't do the table like that. I'm going to show you how to do the table. Here you go. The gravitational force should be to the extreme right and the x here in the middle. That's how you should do it. Here you go. We're going to get, here you go, distance. in meters. I'm not gonna put the unit. Should be 2,000, 3,000, 4,000, all the way down to 10,000. Is that right? Yeah, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. What else? Okay, I'm gonna put an X here. Put the X first. I'm gonna tell you what X is later on. Don't worry about that now. And force. We already measure what this force is. Okay. Expand a little bit. I'm gonna shrink. I hate that. Too small. Can I make it larger? No. Okay, leave this way. Here you go. 18.5 newtons. So 18.5. 3 kilometers apart, or 3,000 meters apart. 7.4 newtons. Now see that the force decreases with the distance. 4 kilometers apart, 4,000 meters apart, 4.2. 5 kilometers apart, 2.7. 6. 1.9. 7. 1.4. 8. 1. 9. 0.8. 10 kilometers apart. Oh, I reached the limit, so I gotta go to the other side. Okay, now I got it. 0.7. Okay. That's the graph you got. Make it look nice. Here you go. I'm gonna put the D separately here. Good. That's the type of table I want. I want the X in the middle. There's a reason for that. Okay, here in this one they put the X in the right side. That's which is a mistake for me. And there's a reason for that. In the space provided in figure 3, make a graph for the gravitational force versus the distance. Plot the gravitational force in the y-axis and the distance in the x-axis. That's what you want to say. That's what you want to do. Let's go. Let's do it. Not this one. On the other one. Force D. Insert. Here you go. That's how the force changes with the distance. Okay? You can go ahead and do the same thing that I did before. I'm not going to do it, okay? Put here the labels in the x and y axis. The y-axis is the force, the x-axis is the distance in meters. Force in newtons, meters, distance in meters. Does it show that inversely proportional? Yes, it shows it's inversely proportional because it's decreasing as the distance increases. If you want to know exactly what is the relation, put like a power PHET and display the equation. Okay, see that? The distance goes with the inverse of the square of the distance. Not exactly the inverse of the square in this specific plot, but it's close enough to what the theory predicts. Is 2% difference, the power here is 2% difference only. Note that we have a negative number. If you want to put more decimal places there, just change the format to scientific with 2 decimal places. Okay. That's the graph you want to do. I'm saving that for you. Any questions? Am I going too fast?
Professor?
Yeah.
Can you show how you added that equation line into the graph?
You mean this equation here?
Or I mean the line that runs to the point?
Okay, so you mean this line and this equation, right? That's what you're asking, right?
Yeah, that's right.
Okay, let me delete that for you. Here you go. We start with the graph. You got that, right?
Yes.
Right? You have it right now. Don't forget to put the labels, right? The force and the distance. Click on the data points. Everything should be highlighted. Right click, add trend line. Remember? Do you see a straight line here?
Oh, okay, and then there are options on the right. Okay.
Huh? What did you say?
Yeah, just notice the options that are on the right side.
Yeah, notice the options here on the right side, right? What you're going to do, you're going to select power. Okay, and then display equation chart, display R square on chart. The power is a negative 2. Did you get it?
Yeah, thank you very much.
Okay. Anybody else?
Professor,
Yeah.
for the one of the data points, I think instead of 18.5, I think it's supposed to be 16.7. So if you have it at 1.9 kilometers, it's at 18.5. But if you move it over to 2.0, it's at 16.7.
Let me see. Let's go slowly here. Which one are you talking about? 2, 3, 4, 5. Which one are you talking about?
The first one for 2000, it's at 18.5. If you go to the simulation, 18.5 is at 1.9 instead of 2. I don't know if it made a big difference or not.
Let me see. Let me go to my Let me go to my simulation. 2,000, 2 kilometers, right? Is 16.7. Did I put 18.5 there? Okay.
Yeah, 18.5 is for 1.9 kilometers.
Okay. So it's 16.7. I put 18.5. Okay. Thank you. Okay. Yeah, it's more difference there. Huh, interesting. You're right. 2 kilometers, 1 billion, 1 billion. Yeah. It's just a big difference. 18.5, yeah, to 16.7. It's like 10% difference. Yeah. But you should get, almost the same thing. It's not exactly. So let me see. I believe there was a big difference here in this coefficient, right? Yeah, the big difference in the coefficient. We don't want number. We want scientific format. Yeah, 6.58. I was getting 9 point whatever. Yeah, thank you. Thank you for letting me know. I don't know why I typed 18.5 there. That's what happens when you start doing things quick, right? Very quickly. And now my power is, 2. Just a matter of increasing. Maybe the decimal places, you can get better values. Let's move forward. 4 o'clock, we have 20 more minutes to go. I think we can finish on time. In the space provided in figure 3, make a graph. Okay, we did the graph. Referring to equation 1, when the two masses are equal, we can here write the magnitude of the gravitational force as gm squared d squared. m1 equal to m2 equal to m. Okay? And now I want to linearize this equation. In order to linearize this equation, I'm going to call FGY. I'm going to call the slope gm square. I will call 1 divided by d square x. And I'm going to put an intercept term here that should be very close to 0. Okay? Like we have right here in this equation. That is my slope. That's going to be my x. And that should be the b. Okay, and now we are going to calculate x and record its value here in this column. That's how we linearize the equation. Okay, here you go. X is going to be the inverse square of d. Inverse square of d. Here you go. Click and drag. Shrink a little bit. I'm going to put one decimal place is enough. A number. Scientific. Yeah, I'll leave 2. Okay. And now we are going to plot this one. When we plot this one, you're going to find out that it has been linearized. It's a linear behavior. Insert 3 graphs. Okay, I want you to do 3 graphs. Okay, see that? We got it linearized. What was not linear before became linear now with this simple transformation. We can add a trend line. It's going to be a linear. Here you go. I'm going to put more decimal places there. Scientific, that's good. I think, can I do better than that? It's too crunched up here, right? I don't like the way it is. We are going to change the axis option. Number. Scientific, I'm going to put just 1 decimal place there. Save space. Otherwise they're not too close. This one's going to be bold-faced, blah, 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 okay? And now we got my new equation. This one is linearized. Let's see what it's asking. Strange. It's not behaving the proper way. I do not know why. Strange. Okay, let's shrink it here. If you're sure you find blah blah blah, you must get linear graph using x. Okay, slope. Put the slope that you got, 6.67 times 10 to the 7th, and then you gotta put the unit there as well. I think the problem is I don't like this. Unfreeze the panel. Okay. Why it doesn't show? Oh, okay, here. That's why. Okay, don't forget the unit. The unit should be the unit of the vertical divided by the unit of the horizontal. Okay? The intercept is this value here. Finding the mass, using the equation determined for step number 5, and the slope of your linearized graph. Find the mass, m1, m2. Okay, so how do we do that? Okay, we're gonna go back here. That's going to be my equation. But now it's gonna be a little bit different. It's going to be what? The slope it's not gonna be, it's gonna be G M1 M2. But don't forget that M1 is equal to M2. Okay? This one is a different exercise. I don't like. The slope that I am getting is, go back, 6.67 times 10 to the 7. Oh, and that you gotta look at the unit. The unit is the unit of force divided by the unit of the x. The unit of x is what? 1 divided by meter square. Unit of force, right? Rise divided by the run. Substitute. Oh, don't worry. We also have that M1 is going to be equal to M2. Alright, I'm going to put it here 1 billion kilograms. M2 is going to be the same value. Substitute. Hey, wait a minute. No, I'm sorry. The way you're going to do, you don't know M1 and M2, okay? We do not know it. I'm doing it the wrong way. He's asking to find M1 and M2, okay? So because M1 is equal to M2, we get this value here. And I want to find out M2, which is equal to M1. Here you go. That's how we should be doing. We use the G that we know. We use the G that we got before. Let's put it here. We use the slope that we got from the plot. Here you go. And we're almost there. Almost there. Expand. We solve for M2. Here you go. I'm supposed to get 1 billion. Doesn't look like I'm going to get 1 billion. Oh yeah, I do get 1 billion. It's not exactly 1 billion. It's 9.9982 times 10 to the 8. It's more like 999.82 million. That's what we're getting. Very small percentage difference. Okay, so here you go. Result and conclusions. Write a brief overview. Okay, we're done. We're done. Let me just summarize what we did for this part. Summary. Summary first. Plotted, kept M1 constant and varied M2. Plotted force in the y-axis and M2 in the x-axis. Okay, that's what would be part 1, right? Part 1. What else? Find the slope. Get G experimental. With the given values of D and M1. Okay, that's what we did part 2. We did 2 things. Here you go. Made M1 equal to M2. Varied D. Plotted the force in the x-axis and D in the x-axis. Don't need to do anything. I'll call that part 2A. And then we did, there's nothing else you need to do here, right? Well, you know, you can do the following. PHET, what the trend line that we fit. We fit a power trend line. And trend line. And see if you get x to minus 2 behavior. Doesn't have to be exactly, but approximately x to minus 2 behavior. There you go. Part 2A, 2B. Made. Yeah. Repeated. Let me see. Part 2B. Made x equal to 1 divided by d squared. What else? Plot. Ooh, I hate that. Plotted f along the x-axis, the y-axis, and x along the x-axis. Get this low, let's see, fit a linear curve. Okay, plot the force. Okay, here you go. Fit a linear curve here too, right? A linear curve. Fit a linear curve. Find the slope and the intercept. Find the slope and intercept. Using, oh, what I did? Very D. Yeah, that's right. Using G experimental in part 1, find the value of the masses. Okay, that's what we did. That's the summary. 4:15 right now. I will save this document and upload to the Google Drive. I have here my recording that I'm also going to upload to my YouTube channel, okay? So that's what we have, folks. So I see you again the day after tomorrow. Okay? So see you.
Thank you, Professor.
Bye-bye.
Thank you, Professor.
Okay, bye. Welcome.
Thank you, Professor.
Okay.
Hi, Professor. You have office hours right now, right?
Yeah, I have office hours right now. Who is that?
Medina.
Medina. Okay.
I'm from group 1, and our group saw the corrected lab 3, and we just wanted to go over the corrections with you and see what we missed.
Okay, so here you go. Let me get some water here first. In your case, it was a numeric value. I remember what was the problem. Here you go. Let me stop my recording here first.